So let's start the second part of today's lecture, the introduction to big data management. In order to know how to manage big data, we need to be familiar with the basic concepts of big data first. So today, I will introduce the big data, and we will leave the introduction to management of big data to Wednesday. Okay. So what is big data? We have this tweeted in 2013, 7 years ago. It was a quite famous tweet and quite vivid about big data. Okay. It says like everyone talks about it. Nobody really knows how to do it. Everyone thinks everyone else is doing it, so everyone claims they are doing it. Well, this is basically true when it was tweeted 7 years ago. But things are changing and the area of big data is evolving. So when we look at this tweet 7 years later, it is no longer that true. And also, Professor Dan Ariely is from Duke University, is not a computer scientist. He is an economist. So his understanding of big data 7 years ago is not touching the essential part of big data. And today, we do have a better and more accurate understanding of big data. It is interesting that although everyone is talking about big data today, many researchers are researching big data. And for example, this course has more than 300 students who is willing to throw themselves to this area. But it is a common sense, at least in database area, that there is no standard definition of big data. And even the origin of big data is unreliable. Here, I quoted 2 paragraphs about big data. One is from Wikipedia, one is from Amazon. And as you can see, in Wikipedia, the big data is defined as a field that treats ways to analyze, systematically extract information from, or otherwise deal with datasets that are too large or complex to be dealt with by traditional data processing application software. The Amazon's definition is the big data can be described in terms of data management challenges that, due to increasing volume, velocity, and variety of data, cannot be solved with traditional databases. If we dig a little bit more on these 2 definitions, it appears that first of all, big data is the datasets or the management of datasets. The characteristics of these datasets is, well, they're large, complex, or in Amazon's definition, they actually use the 3 V's, the volume, velocity, and variety. So this describes what kind of data we're talking about. And both Wikipedia and Amazon mentioned the word traditional, which is also the challenge of big data, because the data becomes bigger or more complex. The traditional methods or traditional softwares cannot solve the new challenges. In other words, when we're talking about big data, we are actually referring, if I would conclude here, to the data sets that has 3 V's characteristics such that the traditional method cannot address the new challenges on these datasets. So I try to explore a little bit more, and we actually get quite similar idea of as the previous one. So here I draw a word cloud, which is generated from the top 20 results when I search what is big data in Google. Here, the larger size of a word implies higher frequency of that word appears in all the 20 results in Google. And I have already eliminated the stop words to make it clearly. Here we can see large sets, data, volume. These are the major characteristics about big data. So we're talking about a big set of data or large volume of data. And structured and unstructured here refers to different types of data, or in other words, the variety of data. Here the increasing and growth, these words describe the generating speed of data. So this is so-called velocity of data. We also have manage, software, process, describe. So these words refers to the major operations when we deal with big data. And these are what we will see more in this course. And finally, the tradition here is what we have mentioned before, the main challenge of big data, or that's why we are taking this course, what we are going to learn. So let's conclude here. What is big data? It's first of all a set of data with special characteristics, including volume, variety, velocity, and many other characteristics that we will mention later. And because of these special characteristics, traditional methods cannot manage it. So the processing here, including store and analyze data, or retrieving data from the data sets, or visualize data, and other applications. Okay, so that is why we need this course to address the above problems. It is interesting to see the definition of big data, of course, the informal definition of big data, or how people describe big data, have evolved rapidly over the past 2 decades. As a matter of fact, big data has been defined as early as 2001. An analyst of META named Doug Laney defined challenges and opportunities brought about by increased data with a 3 V's model, which are the increase of volume, velocity, and variety in a research report. According to my research on the history, the 4th V comes in 2006, appears in the initial version of Hadoop tutorial. And the fourth V is defined as veracity. The fifth V appears in around 2014 in academic papers. It starts to have different versions, but most of them agree on value. Then things starts to be out of control after that. It looks like a competition, and people are inviting more and more Vs. As I can see, 7 Vs, 8 Vs, 10 Vs, 17 Vs, and one recent article actually listed 42 Vs. While it is apparently impossible to cover all the 42 Vs in today's lecture, and also I don't think it is necessary because only the essential Vs matters. So I conclude 7 Vs here, and we will go through them one by one. Here are the most common Vs from different resources I've been seeing. And in this course, we will introduce what these Vs are and what challenges they have brought, and what are the methods or frameworks to overcome these challenges. So these 7 Vs are volume, which is the size of the data or the scale of the data. The variety, which is the diversity of the data. Velocity is the growth speed of data. Veracity is the quality of the data. Variability is how data varies over time. Visibility is the visualization of data. And the last V is the value of data. So we will introduce them, follow this order, and start from volume first. So volume refers to the quantity of data being created from all sources. It is also the fundamental thing of big data, because if we do not talk about volume, then how can we know the data is big, right? So apparently the question here is, how much data do we have? And according to IDC, the total number of data, digital data, I think, all over the world in 2018 is 18 zettabytes. And this number will grow to 175 zettabytes in 2025. Here we have to introduce this new concept named zettabytes, so that we can describe that large volume of data. So 1 zettabyte is 1024 exabytes, which is approximately 10 to the power of 9 terabytes and 10 to the power of 12 gigabytes. If we only use numbers here, it may not be that concrete, say how much data is 1 zettabytes. So let's try to use two examples here. So considering the 175 zettabytes in 2025, if you were to store this much data on DVDs, your stack of DVDs would be long enough to circle the Earth for more than 200 times. And if you attempted to download all this 175 zettabytes data at the average current internet connection speed, it would take you 1.8 billion years to finish the downloading. So yes, the data is extremely large. Now let's see some more numbers from internet. So in 2020, there are in total 4.6 billion people online and 5.1 billion mobile phone owners. There are 2 billion online shoppers and 3.7 billion social media users. You can imagine how much data they would generate every day, or even every minute. In fact, according to the chart here, every minute we would have 480,000 tweets constructed, 4.7 million videos viewed in YouTube. There are 60,000 images uploaded to Instagram and 4.2 million search queries in Google. 200 million emails are sent in every minute. And please remember, these are only data from social media, and we also have data from e-commerce, from financial services, from healthcare, and many other departments or many other businesses. Therefore, the volume of data today is definitely unimaginable. Well, compared to the characteristics, it is more important for us to know where the challenge is. For volume, the immediate idea of challenge should be the storage. Here, recall the challenge is the old method or the traditional method or framework cannot adapt the new big data case. So in order to address the challenging regarding volume, let's see an example here. So here I listed some parameters of different models of Macintosh PCs over the past 40 years. Since we're talking about storage, so all I care about is RAM capacity and the capacity of disks. So in 1990, the RAM is between 1 megabyte to 4 megabytes, where the disk, well, you can choose not to have a hard disk, or you can choose at most 40 megabytes hard disk. In 2000, the maximum capacity of RAM is 1.5 gigabytes, and for a hard disk is 60 gigabytes. In 2010, the number of RAM increased to 16 gigabytes, while we would be able to have a 2 terabytes hard disk. And in last year, the number of RAM is 64 gigabytes, and the number for hard disk is 3 terabytes. It looks like the capacity of both RAM and hard disk grows rapidly over the past 40 years, but the data increases much more rapidly. According to Eric Schmidt, who was the CEO of Google, between the birth of the world and 2003, there are in total 5 exabytes of data had been created. And according to Wikipedia, the world digital data achieves 1 zettabyte in 2012. So remember, 1 zettabyte equals to 1024 exabytes. Okay, and in 2019, the total number of data in the world would be around 40 zettabytes. So the growth of storage capacity is way behind the growth of data. And in 1990, we can easily store a database in a floppy disk. And in 2000, we need a storage server with multiple hard disks to store a database. And we start to move data to clouds in 2010. Now, what shall we do for the future? Because apparently we need something new to deal with the challenging brought by the volume of big data. Interestingly, this is not the only challenge that's brought by the volume of big data. For example, the time complexity for many algorithms are also affected by the big volume of data. For example, the sort algorithms, most of them would have the time complexity of n log n, which is superlinear. And if we consider the join operation in database management system, it is more interesting. So basically, because the table is not small, so hash join is infeasible. And nested loop join is infeasible as well, because we would have both tables to be joined are large. So in this case, the best choice would be sorted merge join. And if we don't consider using an index here, the time complexity would be big O of n log n plus m log n, where n is the size of table 1 and m is the size of the other table. If we consider shortest path algorithms, we consider direct graph with non-negative weights. Then in this case, the Dijkstra algorithm has the best big O notation of time complexity. And if we use a binary heap here, the time complexity would be v log v plus e log v, where e is the total number of edges and v is the total number of vertices. In the big data background, for example, if we consider a social network, then the number of edges and vertex are both quite large. So this algorithm also, the time complexity is going to be quite huge. And if we consider nearest neighbor search in high dimensional data, because of the curse of dimensionality, which will be mentioned in later in probably week 4 or week 5, the time complexity would not be sublinear. So the best we can do is linear search, which means the time would be big O of d times n, where d is the dimensionality and n is the number of points in the data sets. And this is only for you to find the nearest neighbor of the query. Not mentioned, there are a lot of NP-hard problems there. And so basically, when n comes larger, none of these algorithms has a sublinear time complexity, means the time complexity would grow faster than n. That's why all of them would suffer from a large n, from the large volume of data here. So basically, when the volume of data increases, the performance of these algorithms decreases and the cost increases. So that is not what we want to see. And that is why we need to do something to over the big volume of data here. All right, now let's look at the second V, which is variety. So variety refers to the diversity of data. There are many different aspects to describe the diversity of data here, but we are mainly focused on two aspects. One is different data types, and the other is different data sources. For different data types, we have relational data, which are tables and transactions. These data are the traditional database data. These data are the data in traditional databases. I think you've played with it in database systems course. And text data, including books, reports, or your email contents. The difference between text data and the relational data is that relational data is structured. So we have a fixed schema, while the text data is totally unstructured. And we also have some semi-structured data, such as the JSON data, XML data. Semi-structured data does not conform to relational databases, but they still contain some level of organization through semantic elements, such as tags in XML or in JSON files. In addition, we have graph data, which is generated from social networks or from RDF, and we can't ignore image and video data here, where we can get them from many places, but mainly from internet, including Instagram, YouTube, Flickr, such kind of websites. Apart from different types, data also have different sources. For example, for one movie, the reviews could come from IMDb and Rotten Tomatoes, and for the same product, the reviews could come from different providers' websites. Also, for a human being, the personal information comes from different social applications. Okay. And since could be more complex, for example, a single application can be generating or collecting multiple types of data. For example, emails and web pages. Let's take email as an example here. So in an email, we have the sender's information, the receiver's information, the date. These are structured data. And we have the body of the email, which is text, which is totally unstructured. And in the attachment, we could have image or multimedia. So these are also unstructured data. And same things happen in web pages. On the other hand, if we want to extract knowledge, then all the data with different types and sources need to be linked together so we can get a better understanding of the knowledge or what we want to know. For example, here is when you want to profile a customer. You can collect information from different sources, and of course, I mean, they are in different types. For example, in addition to the customer information you have already got, which is stored in your database, you would also be able to have the banking financing information from the MasterCard or its bank account. You could have his purchasing history from eBay or Amazon or other e-commerce websites. You could know what video he liked to view or what game he likes to play, and also the social media accounts of the customer from Facebook, Instagram, tweets. You could collect different kind of information here. Some of them are text data, some of them are logs, which would be like streaming data, and some structured data in the database. Some are multimedia data, such like the videos or movies he has been viewing. Well, it looks like it's good to have this much data, but remember, you need to extract useful information from this massive data, and this much data brings incredible troubles for the traditional methods when doing such. So, what is the challenge here? Let's consider two different tasks. One is data integration and the other is data creation. So let's first discuss data integration. So the major problem when we're considering data integration that is brought by variety is heterogeneous. Data integration is the process to combining data from different sources into a single unified view. And heterogeneous means the schema of the data are quite different from each other. So in order to overcome this problem, the traditional method relies on schema mapping. So schema mapping, the idea is to find a mediate schema such that the heterogeneous data can be unified. Apparently, the difficulty and the time complexity is highly related to the level of heterogeneity and the amount of data sources. Also, it is related to the volume of data as well. So apparently, when we talk about variety, data comes from different sources, have different types. The heterogeneous is quite serious problem, where the traditional schema mapping no longer works. That's why we need to find a new way to do this job. Also, the record linkage in variety data is also challenging. Record linkage, the task is to identify whether two records are referring to the same entity or not. Since now we have data with different sources and different types, it seems that we can do more, but the fact is the difficulty increases as well. We need to make use of different types of data or information here from different sources, but we also need to properly handle this data with different types and different sources. So that is also challenging. The data curation task is to organize and integrate data from collected from various sources. And here we are facing a long tail of data variety problem, which shows the importance of data curation, but also brings more. Here we can see the trend of expanding the data from left to right, where towards to those data that is towards the data that is less frequently used, that is more decentralized and more unstructured. While the frequently used data usually have consistent schemas, have centralized generation, and usually relational tables in database, this long tail of less frequently used data actually allows data consumers, which are those who use the data, to have a more comprehensive model of their domain that can be searched or queried and analyzed. But as you can see in the figure, the consumption cost grows rapidly. So this is how data curation can help to reduce the cost and brings the consumers a better experience. Now, here comes the third V in big data, which is velocity. So velocity means speed. In the background of, in the context of big data, data is being generated fast. Therefore, it needs to be stored fast, processed fast, and analyzed fast. So here are some numbers to show how fast data are generating every second. So every second we will have nearly 9,000 tweets sent. We have nearly 1,000 Instagram photos to be uploaded. We would have more than 4,000 Skype calls, have 93,000 gigabytes of internet traffic. We would have 83,000 Google searches, and we would have 2.9 million emails sent in every second. And still, please note it, this is only the data from internet. We would have more data generating every second in laboratories, in governments, in companies, so on and so forth. Now, the reason of the growth of data comes from different aspects. For example, the users in internet, it comes from 16 million in 1995, linearly growing to 3.4 billion in 2016. So the users of internet are linearly growing. This implies the exponential growth of data volume. Okay, and the Internet of Things. The Internet of Things refers to the billions of physical devices around the world that are connected to the internet, such as sensor devices and surveillance cameras. These devices keep sending and receiving data. So, Internet of Things generating large amount of data every second. And most importantly, most of them need to be processed at real time. Consider of your sensor. Consider of the cameras in your house, or the surveillance cameras in the street. The data needs to be processed in real time, such that the criminal can be prevented. The cloud computing. The market of cloud computing grows from $26.4 billion in 2012 to 10 times in 2020. So you can imagine, this means how much data is uploading and downloading, uploading to and downloading from the cloud every day, and how it grows. Okay, and for website, we have 156 million websites in 2008. Now the number is 1.5 billion in 2019. So this growth of websites brings the growth of data as well, of course. And don't forget the scientific data. For example, we collect weather data every day, and the laboratory will generate a lot of data, and this data need to be processed fast to support the research. So basically, data is now streaming into the server in real time in a continuous fashion, and the result is only useful if the delay is very short. There are many applications need immediate response. For example, the fraud detection for your credit cards, and the healthcare monitoring that monitor your health condition. They need to respond immediately if the signal is detected. And also for business, this kind of real-time response is also important. For example, this is a true story. Well, the Walmart's real-time alerting actually helped Walmart to increase its revenue. So the story is that one year the Walmart was able to identify a particular Halloween cookie that was popular in most of its stores, except for 2 locations where it wasn't selling at all. So a quick investigation at those 2 locations shows that the cookies weren't yet on the store shelves. So Walmart discovered this and put the cookies on the shelves and helped the selling. So you can imagine if Walmart discovered this stocking problem after Halloween, the values of this insight would have completely vanished. Therefore, this real-time processing is really important. So again, what is the challenge of velocity? So as we have mentioned before, the real-time processing is very important to handling this velocity characteristics of big data, but the traditional way of processing data is based on batch. So basically you would collect the data and clean data, feed them in chunks. The data you collected could be over years, a lot of data to help you make the decision. So after you feed them in the trucks, you wait for the new data comes in, and for a fixed amount of data, you act, you do the prediction, or you make the decision. But for real-time processing, things change. So basically, you capturing the streaming data, and you feed them in machines in real time, you process them in real time, and you act immediately. So it is completely from batch processing, which means we need new technologies to support this real-time processing frameworks. Also, transmission could be another problem. Transferring data becomes a prominent issue in big data because the generating speed of big data and the need of processing data in real time. Therefore, the problem is how do we balance the latency or bandwidth and the cost during the transmission, and also the reliability of data transmission. These issues are easy to overcome when the data volume is not that large, or the response time is not that short. But because of the volume and the velocity of big data, now we need to design new methods to overcome. All right, let's stop here for today. And on Wednesday, we will finish the rest with in big data. And I will briefly introduce the idea of big data management. So see you on Wednesday.